let's say we are full of motivation and want to build a new app. We want to develop a new app which takes a drawing of the user, hand drawing of the user, like this. This is a drawing, and outputs the number of percent to which we believe that this is an apple. So the percentage of the confidence that drawing is apple. Do you know similar apps? Are there apps like this around? Sorry? Hot dog or not? There's really an app, hot dog or not? Okay. So we now come up with a new idea. We now do this for apples, because there are so many apples around this year. As you might have noticed, when you look at the apple trees, they are full of apples. So now we come up with a new idea, a new business idea. We want to develop an app which takes the drawing of a user and tells him how good he was in drawing an apple. Let's now start to formalize this as a machine learning problem. What is a data point here? What could be a data point? The drawing. A drawing is a data point. Can everybody see or understand my drawing? Everybody understand my voice? Should I speak louder? Let me know, please. So a drawing is a data point. What are the features of a data point? Let's say he draws, or we read in the drawing as a black and white bitmap with dimensions 16 pixels width and height. 16, here also 16 pixels. What is the feature, what could be the feature vector for such a data point? Well, we could take each pixel, each individual pixel, and then set a 0 at the corresponding entry of the vector if there is no ink, or we set 1 if this pixel has ink. So this here might be here, is 1. So we get a vector full with zeros and ones, depending if a pixel is black or white. How long or how long is this feature vector? What is d? 16 to the power of 2. So that's the input, the feature vector that describes the data point. What is the label here? What is the information we are interested in? Inked or not? Well, this inked or not, we have here in the features. These are the features that we can determine easily. Features we can determine easily. Yeah? Is it apple? Yes. So we could use as the label of the data point either apple, or we say no apple. So the label space here would be binary, either apple or no apple. We could encode this as -1 for apple, +1 for no apple, and so on and so forth. However, we want something different here. We want to tell the user the extent or the confidence that his drawing is an apple. So we don't use binary labels, which would yield a classification problem. This we'll discuss next week, but today we stick to regression problems. So we say the label is the confidence on a scale 0 to 1 in drawing is apple. Or confidence or belief that the drawing is an apple. Okay? So the feature space, the set of all possible values the feature vector can take on, is in this case, what would be a feature space? So this is the feature space here. What could we use as a feature space? Well, one option would be we represent the zeros and ones here as real numbers, and then we have 16 to the power of 2 equals 256 real numbers, and this is r to the power of 256. Okay. What would be the label space? The set of all values that the label can take on. All real numbers 0 to 1, or let's be a bit more generous, let's use all real numbers. Okay, so we now identified the feature space and the label space. Now, how do we determine, how do we find out the label y? This is typically unknown. This is what the app has to deliver. This is the job of the app, to estimate or to find a good approximation of the true label. So a drawing has a certain true underlying label, like the confidence provided by 10 or 100 painters, professional painters, Picassos. This is expert knowledge. They could tell you the confidence is 0.6 or 0.7. But we don't know this. So we have to come up with an app that allows us to predict the label or to estimate the label based only on the features. So what we have to build is a mapping or a hypothesis map, let's call it H, which takes the feature vector as input and outputs a guess or an estimate of the label y hat, which should be as close as possible to the true label. So this should approximate y. So on this hypothesis, we can implement, for example, as a Python function or a MATLAB function, let's call it confidence in Apple, confidence in Apple, which takes as input a vector x and outputs at some point y hat, the predicted label or the predicted confidence. And what comes in here? Here is the gap that you have to fill out as a developer. So what comes in here? This defines then the mapping, the hypothesis map. So in machine learning, we do the following. We try out a whole bunch of maps. This bunch of maps is called hypothesis space. So we try out a whole bunch of maps. So here we have some map H1, which takes the feature vector and outputs some guess for the label. We have another map H2, and all the possible maps that we can allow is called the hypothesis space. So how many possible maps are there which take a feature vector as input and output a real number? So the hypothesis space is a bunch or a set of functions which map the feature space into the label space. So this is math notation. I cannot help you you have to dig through this. This math notation, how you write down a function or a map, we need in this course. So how many functions are there which map the feature space, which is in our application r to the power of 256, to the label space, which is r? How many such functions would there be, theoretically? What is the maximum number of functions? Infinite, yeah. It's too big, and everything is too big. In machine learning, also this vector, it sounds not too large, but a 256-dimensional vector is already large. If you want to play around in your programming environment, every naive way of defining a feature, like stacking the pixels into a vector, the vector is too large. And not only the vector is too large, but also the set of possible mappings that we could try out is way too large. It's infinite. So what do? We reduce the set of all possible predictor maps that we would like to consider. So the hypothesis space is typically a subset of all possible maps from feature space to label space. And a good part of machine learning science or engineering goes into clever way or efficient ways to determine how to choose the hypothesis space. This is highly non-trivial. There are certain choices which have established to work well in many applications, like today we look at linear regression. Linear regression is based on the following hypothesis space, which we denote HD, D for dimension. And this is the set of all mappings which are of the following form. They take the vector x, the feature vector x, and multiply it with some weight vector w. This weight vector has to have the same dimension as the feature vector, of course. And this defines a subset of functions from feature space to label space. What is nice about this particular hypothesis space that each element is identified by a weight vector. So we write this as superscript w to indicate that the whole function is fully specified by the weight vector. If you tell me the weight vector, I know everything about the function. Okay. We say we can parameterize this hypothesis space using a weight vector. So each element in this hypothesis space is characterized by a particular weight vector. So this has weight vector 1, and here we get another function by choosing some other weight vector, w2. So this hypothesis space, how large is this hypothesis space? It's now smaller. It's a subset of all possible maps from feature space to label space. But still, how large is it? This linear space, or this space of linear mappings? Yeah. Infinite. Still infinite. Still infinite. However, it has the advantage of allowing for parameterization. So we can search around this. Remember, in machine learning, the idea is to try out many different hypotheses and pick the best. So we have to search over this space fast, or we should be able to search over the space fast. And if we have such a parameterization, we can search fast by adapting the weight vector. By changing the weight vector, we can try out different hypothesis functions, and we can do this fast, quickly, as we will see. So we will now focus on this linear regression model or this hypothesis space underlying linear regression. And let's say we pick one particular such function out of this hypothesis space. For example, let's say W is the vector which has the first entry 1 and the remaining entries all 0. Yeah. Is there anybody which does not understand this notation? Is there anybody for whom this, what I write here, is like hieroglyphs? This is linear algebra. So this you should have learned in a linear algebra course. And this is a bare necessity for doing machine learning at the level that we consider here in this course. So you should be familiar with the notions of vectors or matrices. Okay. So let's say we have a particular function. How can we assess how good this function is for our purpose of predicting the confidence in the drawing being an apple? So how good is it? We can implement this function. So this function we can implement easily. Such a function we can code in one line in Python or in MATLAB. We can just compute the inner product here and output this inner product. So we read in a feature vector. We get the feature vector from the drawing, multiply it with the weight vector, and get an output. So this is called the predicted label, or the prediction, the predicted label, or prediction. Yeah, so we can do this easily. You give me a vector. I use whatever programming language I have. I compute this inner product and can implement the function. How can I tell if a particular function with this particular weight vector is good? What do I need for this to evaluate the quality of a function, of a predictor? The loss function. That's where the loss function comes into play. And in linear regression, we use a particular loss function. We use the squared error loss. So the squared error loss tells us if I have a data point with feature vector x and true label y, and I apply a predictor to it, the loss that I experience when I use this particular predictor to this particular data point is, so the loss, I call it calligraphic L, because I like these fancy letters, and because they are used often in the machine learning literature. So the loss is the predicted output minus the true label to the power of 2 squared. Squared error loss. This is the error. The error, why? Because it is the difference between, let's see, use some colors here. That's not too much. Because this here is the predicted label, the predicted confidence that this drawing is an apple, and this is the true label. And the difference between those two is called error. Then we square it, and this yields a loss, a measure of for the error, for the size of the error that we incur when we use this predictor. It's important to note that I can only evaluate the loss function. The loss function only helps me when I have labeled data available. I can compute the loss only if I have here the true label. If I don't have the true label, I can define whatever loss I want, but I can never evaluate it. It doesn't help me. So in order to evaluate the loss, I need labeled data. Where do I get this labeled data from if I don't have 100 Picassos at my disposal to evaluate the hand drawing, if this is an apple or not. Where do I get the labeled data from? From previous measurements? Who did these previous measurements? Sorry? Trial and error. No, we need the labels. So some expert has to tell us what the labels are. There's no trial and error. We need an expert which tells us this drawing here of mine, this is an apple with 99.9%. So who gives us the labels? I have shown you one online shop for labels. The Mechanical Turk, Amazon Mechanical Turk, is something like a shop where you can buy experts, like 100 Picassos, which look at your drawings and come back, they deliver you back the confidence that this drawing is an apple. Or, and that's why I choose this apple drawing application, there is this tool called, or app called Quick Draw. How many of you know Quick Draw? Yeah, you can Google it, Quick, Draw. And this is an app or a game where you ask as a customer to do some hand drawing, and it tries to find out what did you draw. You can also use it the other way. So this app collects data and provides it to everybody. It's an open source project, so you can then look at all the drawings that the people delivered for the term apple. And you can download this. So this is, I think, on a GitHub. Here you have get the data. Yeah, and then you can read the how-to and download all the drawings of an apple. And maybe there's also some, behind there's some more information. So there's always a tag with more information. And in this tag, I guess there will also be an information that tells you the confidence or how good this drawing was, or how well this drawing aligns with all other drawings of an apple. And you can use these numbers as the label, as the true label. So the labeled data you get from this app. And this illustrates a nice aspect of modern business where people develop apps or develop products not to make monetary benefit, but to collect data. So I've heard about products that are developed not to make a profit, but to collect data. So they take into account that this will cause some loss. This will be a negative business. Yes?
So I would guess since you have some kind of human authorization on the internet that you're not fluctuating, so you'd have to collect it on every square that has, let's say, people in it or traffic lights in it. So would you say that could be used in the same way as well?
Excuse me, what could be used?
So let's say you have an interface, and input where is you can prove that you're a human, right?
As to what?
An input page, and you need to prove that you're a human, you're not a robot, right?
Yes.
So some of them work in a way that they show you a picture.
Yeah.
And then you have to click on every square that has, for example, cars.
Yeah. Yeah, so for the comment was very good. Yeah, this authentication systems where you are provided a bunch of natural images, and you have to choose which image show a certain object, for example, an apple.
You label their data.
You have to label the data, and this is based on the fact that humans are still superior, or in most cases superior in labeling data compared to robots.
And this is an effective way of collecting data.
Yeah.
Without trusting it.
Yeah.
It has some kind of reason for it.
Yes. So there are many, many ways to collect data, and they are so clever that you don't realize it. Basically, any web page that you visit collects some of your data. So you are used, or to some sense abused, as a data generator. And the question is, how much should you benefit from the value that's produced out of your data? Whenever you press a like button somewhere, you produce data and you produce some value. But currently, I don't think that that the users are participating in the gain that is made, in the economic gain that is made from the data that we all produce. And but this is kind of the kind of no or political neutral example of how to collect data by doing a game. By using a game to collect data from the users, from the participants in the game. And we can use this And this is very kind. So the data is made available. We can use this for our app to find the label, the true label. So we have a bunch of data points for which we know the label. Any questions up to here? Okay, so we have worked through this application. We have specified the features. We have specified the label space, real numbers. We have specified the hypothesis space. We want to use only these linear functions. We have specified the loss function. We want to measure the quality using the squared error loss. This constitutes a complete specification of the machine learning problem. Why do I stress this out, the specification? Because basically, when you have managed to come up with such a specification and you are a business person, you can go on to the engineering department and hand over the specification, and he or she knows what to do further. So we now take the perspective of an engineer. Now we get the specification, and we get some labeled data, labeled training data. Yeah?
Can we change this loss function? For example, instead of our 2, we use, for example, our 4.
Yes. So the question was, can we use another loss function, for example, power of 4 instead of power of 2? And this is possible. As I said, what loss function you use is completely up to you. It's a design choice. So if for ever some reason you want to use power of 4, you're allowed to use power of 4. This might, so yeah. Then of course there come aspects of statistical properties that are related to the nature of the data. So for some data, or if you have only little data, this power of 2 might be better than power of 4. Or you have computational infrastructure. You have currently MATLAB. Everybody uses MATLAB in your company, and MATLAB is able to work better with the loss power of 2. So you have to take into account your computational resources. But in principle, formally, you are free to choose whatever you want as a loss function. It's all, yeah, the question was, would be the absolute value better as a loss function? Yeah, in some cases, yes. It's more useful. However, when you use the absolute value, what you get is a non-differentiable function. So the absolute value looks like this. And at this point, basic optimization methods fail, like gradient descent, which we will discuss later on, because here is no gradient. It has an edge. In contrast, the squared error loss is a very nice curve. It's a bowl-shaped. So this is the squared error loss. It has two very nice properties. It is convex, a convex function, and it is differentiable. And whenever you have a convex and differentiable cost function, you can optimize, or you can search over the hypothesis space fast by gradient descent. So this allows to use gradient descent. We will talk about gradient descent later this lecture. So, as I said, we now want to find the best map. We want to find the best map which yields the smallest loss. For evaluating the loss, we need labeled data. Labeled data, which is also called training data, because we use it, this data, to train a good predictor. We get this labeled data, for example, from QuickDraw. We download from QuickDraw a bunch of images, of drawings, with feature vector x, x1, and label confidence in the drawing being an apple, y1. So this is the first data point, up to x, capital N. Throughout the course, we denote the number of label training data points mostly using capital N. So capital N is the sample size. How big is this? What sample size do we have? Well, look at quick draw to get an idea how big the sample size can be. Here we have 140,000 apple drawings. So 140,000 is a typical number for capital N. For example, 140,000 if we use quick draw as a database. We can apply now a given linear predictor to all this data. Yeah, and I use the calligraphic X to denote the collection, the ensemble of all data points. So we can use it to apply, to evaluate the quality of a particular predictor. We just compute the average loss over all labeled data points. So 1 over n, I equals 1 to n, yi minus w transposed xi squared. And we call this average loss empirical risk. This is empirical risk. Empirical risk. We usually denote it like this. It depends on the hypothesis map and on the data set. So that's why I denote the empirical risk like this. So it depends on the hypothesis, which we evaluate currently, and on the data set on which we evaluate the hypothesis. This is the empirical risk. It is the sum or the average of the losses. This is the loss for the ith data point. So let's illustrate this more visually. Let's assume this feature vector x has only one, or let's represent the feature vector x using the x-axis of this diagram here and the label on the y-axis. So we can then do a scatter plot, which you have been asked to do in the first exercise. So we can do a scatter plot where we can draw the data points conveniently. So this might be x1, y1. Then we have another data point here, 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 here. Each cross represents one data point. We have in total 140,000 data points. So I will not draw the complete scatter plot now because I would have to draw 140,000 of these crosses. And what we now do when we evaluate the quality of a particular predictor, so how does this predictor map look in this scatter plot? Well, it's a linear function, so it's a linear curve, a hyperplane in several dimensions. So this here is the predictor. And we look at a certain data point, for example, the first one, and calculate the difference here. So this is the error incurred for the first data point. So this is a bit finer here. This is y1 minus the predicted label for the first data point. So this difference here is the error for the first data point. And we square it to get the loss here. And then what we do, we average all the squared errors over the data points. So that's what's going on here in this formula, in this equation. So we compute the average distance between the data points and this predictor curve. Yeah?
Why do we take the vertical distance instead of the distance in the line? We assume that there is no error in the x-axis?
So why, the question was, why do we take this distances and not this distance?
The minimum distance to the line. So it's like the perpendicular to the line.
To the left.
To the left line.
Ah, this difference. Yeah. We could also use this. This would amount to a different loss function. So the question was, why do we use this vertical difference or the vertical the length of the vertical segment and not the kind of the distance to the hyperplane. This would also be possible, but would result in a different loss function, which is might be not that easy to optimize. We will see that this squared error loss can be optimized easily. Okay, any other question? Yeah? So the question was, does the loss function have to be differentiable, or is differentiability the main criterion for choosing the loss function? It is one important aspect. A main method for optimizing, for minimizing loss function that we will discuss in this course, and which is underlying many, many methods currently in machine learning, is gradient descent. And gradient descent in its standard form only applies to differentiable functions. However, you can come up with sophisticated optimization methods which work well also for non-differentiable loss functions. It depends on your particular hardware that you have. So the general rule is choose the loss function that you can optimize it efficiently using whatever you have at your disposal. And when you have at your disposal only Excel spreadsheets, and you can do machine learning with Excel, just Google it, then differentiability is not really an issue. In Excel, you just do a grid search. You search over all possible points and pick the smallest one. Okay. So differentiability is one aspect, but it's not the unique relevant aspect for how to choose loss functions. Yep. Any other question? What is the practical use of this loss function? The practical use, it requires, so in this case, it steers the search of the machine learning method towards predictor maps which make this error small. So that the predictor agrees with the confidence that a Picasso would tell you. Yeah. Yeah, but in the end, it's up to you how you want to define the loss. What it means for your particular application if a predictor gives you a label y hat, but the true label is something else. You can come up with any fancy loss function definition. But this is reasonable since this squared error loss requires that the error, the difference, or the magnitude of the difference between the predicted label and the true label is small. But this might not be relevant for some applications. It might be irrelevant for some applications. However, it has turned out that in many useful applications, this loss is useful. That's why I now start with this loss function, but I want to highlight again, in the end, the loss function is up to you. You decide, as a machine learning engineer, what loss function to use. Yeah, for example. So the question was, could it be that the customer gives you the loss function? And this is actually the best case, which I would not hope for in general if somebody tells you what loss function to use. Often, nobody tells you what loss function to use, but the business person just tell you, we want to have this or that customer experience. Okay, so now we have evaluated one particular predictor map. Machine learning now is about to find the best predictor map out of all possible predictor maps. So find HW belonging to the hypothesis space that we use, such that the empirical risk is minimum. Does this make sense to you, this program or this objective? Yeah? So this is the empirical risk minimization principle, and we now do nothing but translate this principle, this goal, into some math. So we just write, this is then called the empirical risk minimization problem. Minimize by choosing different hypothesis maps out of the hypothesis space the empirical risk. Okay, that's it. That's the problem that we have to solve. So machine learning amounts to solving an optimization problem. If you're good in optimization, you have very good premises to do good machine learning methods. That's now nice, but how do we solve it actually? Well, let's insert what we have for the empirical risk. So the empirical risk for the linear regression model is 1 over n, sum over all labeled samples, over all labeled data points, yi minus w transposed xi squared. And it turns out that this objective function, so let's call this f of w. So this is a function that depends on the weight vector which defines the hypothesis. So when we search over the hypothesis space, we try out different, so we change this w vector. We tune the w vector, try out different vectors. By using different vectors for the weight, we move along, we search over this hypothesis space. So we want to minimize, we want to find that particular weight vector which minimizes this empirical risk. We can, since we represent any function in this hypothesis space by the weight vector w, we can forget about minimizing over functions and say, let's just minimize over the weight vector. This looks a bit nicer in math terms. Okay. How many of you think they could solve this optimization problem? This is a nice optimization problem. It amounts to minimizing a convex differentiable function of the weight vector. So if we draw this FW, it looks like this. It's bowl-shaped, bent upwards. It allows to compute a derivative or a gradient at each point. For example, here. Let's call this weight vector W0. So we can compute the weight vector here. We can compute a gradient here. Gradient of this function at point W0. And yeah, how do we find the minimum? How do we find the best weight vector? Let's call this W optimal. How can we find the weight vector which minimizes this expression here? Yeah?
Well, basically just take the gradient from each point and then move towards the gradient.
Yeah.
The step size is dependent on the user expression operation.
Yeah.
And until we reach the point where the gradient doesn't, then it changes its size.
Yeah. So the idea, and this is called gradient descent, let's start with some weight vector W0. So you start with the search. Remember, machine learning is about searching over the hypothesis space, over the bunch of possible predictor maps, and finding the one which has the smallest error. So we start at some point, HW0, and then how should we move on? What's the next one? And this tells us the gradient. So the gradient here tells us we should be here. So the next one is here, W1, the next guess. And it's given by the old vector minus, now comes a correction term, alpha times the gradient of the objective function. So, this is called gradient descent. We go down the gradient. Gradient descent step, or downhill. And it turns out if you repeat this, so if you start with W0, use gradient descent to get W1, use another gradient descent step to get W2, and so on and so forth. You do this k times. Then this sequence of weight vectors, or this sequence of search points in the hypothesis space, they converge to the optimal weight vector under some conditions, which I tell you later. So that the limit of the sequence is the optimal weight vector. Yeah, and we basically have our first machine learning algorithm, which is gradient descent linear regression. This you can implement in a programming language, run it for several times, for a sufficient number of times, and in the end you get a weight vector. And this weight vector that you get, hopefully close to the optimal weight vector, or let's call this WK. This defines a predictor, a linear predictor, and this linear predictor is the point in the hypothesis, is the point we were looking for. So this is the goal. Here's the optimal predictor. That's the treasure that we want to find. And using gradient descent, we come gradually closer and closer to this optimal point. That's the basic idea of machine learning, or many machine learning methods nowadays. They are based on variants, more or less straightforward variants of gradient descent. Many methods in deep learning use gradient descent. What is different between these methods is the hypothesis space that they use. In this case, in this simple example, we used the space of linear mappings. Another example is to use the space of all mappings that can be represented as a deep neural network. So a deep neural network is nothing but a specification of a very complicated space of functions. And we will have a guest talk by a teacher which talks about how you do gradient descent for deep neural networks. So that's why I don't want to talk about too much here. For now, it's important to note we can do this gradient descent steps repetitively. We iterate this gradient descent steps, and we will get closer and closer to the optimal weight vector. If, and this is important here, if this step size, so this is a step size parameter, alpha, is chosen not too large. So we have to make sure what can happen in gradient descent if we choose the step size too large, alpha too large, then we could start very close to the optimal point already, but overshoot. So the gradient descent step would yield us here and then we move uphill, we increase the objective function. So if alpha is too large, we might not get anywhere close to the optimal point, but move away actually from it. The other problematic case, if alpha is too small, if the step size is too small, what happens here? Well, we make only very, very little progress in each iteration. So it takes forever to converge. Very little progress. In iterations. So if alpha is too small, if the step size is too small, what happens in this hypothesis space picture, which now evolves really nice, we move too slow or very small steps. It takes forever and 3 days to get anyhow close to the optimal point. It's also not useful nowadays. Time is money. So choosing the optimal step size is one of the key, if not the key issue when you apply gradient descent. There are sophisticated methods I have discussed this in the course book, so if you want to read more about gradient descent, have a look at the course book. And I also discuss how to choose alpha, so which values you have to choose to ensure that these gradient descent iterations converge. Okay, I now suggest we have a 10 minutes break and then continue with discussing how complicated it is to implement actually gradient descent. Sorry? Yes?
I'm from the Alba AS side. I'll actually send you an email. Oh, this guy.
Yeah.
And you,
Hello. Nice to meet you.
nice to meet you. So, we are. Do you remember anything about our thing, the club or anything? Okay, so we are having our fall kick-off sauna next week on Friday. So, could it be possible for me and my colleague to give a short advertisement, let's say next Tuesday on your lecture or next Friday on your lecture?
Yeah, next Friday I would.
Yeah, that'd be cool.
Sure.
Yeah, perfect. Thank you. So we need about 5-ish minutes to represent the club and everything. Yeah, thank you very much.
Are you also in connection with the auto analytics?
No, I think we're focusing on the business aspect of machine learning, whereas we are focusing on the scientific aspects.
Okay.
Maybe I'll say you.
Yeah, it only works if you. So let's continue our discussion with how to implement gradient descent for our app. How to draw an apple, or let's draw some apples. The goal is to find a predictor which allows to take the input features, which is the drawing, or which are the pixels of the drawing provided by a user, and outputs the confidence that the drawing is an apple. So we want to get a mapping which takes the feature vector x as input and outputs a predicted label, y hat. We decided to go for linear maps. So we reduced the space of all possible maps from features to labels to the subset of linear maps. This is the hypothesis space underlying linear regression. And then we decided to measure the quality of a particular map using the squared error loss. So the name of the game is minimize or find the particular linear predictor that minimizes the average loss or the empirical risk incurred over labeled training data. The labeled training data we get, for example, using the Quick Draw app. So the machine learning problem has boiled down to an optimization problem here, a minimization problem, which we can solve using gradient descent. So I write out again gradient descent. Gradient descent. Starting from some initial guess for the optimal weight vector, which we might generate at random. We construct a sequence of increasingly more or better weight vectors by taking the previous guess for the weight vector and going into the opposite of the gradient by a step size alpha. In order to code this in Python or MATLAB, we need to work out the gradient of the objective function. So the objective function was this here, the sum of squared errors. Let's write it down again. So fw was 1 over n squared. What is the gradient of this function? So this is kind of one of the bare necessities. I don't want to be the party crusher here, but you should be able to compute the gradient of this function, or at least understand in rough terms how I get the gradient. And the gradient is, as you might confirm, 1 over n. The sum again, transposed xi. Okay, that's the gradient. Yeah? Yes? We have to put a 2, yes. This is not the gradient. We have to put a 2. Anything else? We have to put a minus, yeah. Okay. So, anything else? We take the derivative with respect to w. Yeah. xi. Yep. Anything else? Do we stabilize? I think so. Okay, this is the gradient. And now let's plug in the gradient here to get the more explicit expression for gradient descent. Minus alpha plus alpha 2 over n 0 times xi. So the update, so this is the update or the correction term that we apply in each iteration of gradient descent. There's a correction term. And this correction term has an appealing form because it's a weighted sum of all the feature vectors. So this W vector is a blend or a mixture of all feature vectors that we have in the training data set, and each feature vector is weighted by some weight, and it turns out that this here is the error of a particular training sample. So this is the error of the ith training sample, and we see the larger the error, the more weight the corresponding feature vector receives. And this is somewhat similar to this learning by trial and error. We try out, okay, here, I forgot, we use the weight vector of the previous iteration. So this here means try out the predictor of the previous iteration. Then compute the error, and based on the error, update the new weight vector, which defines the new predictor. So this new weight vector defines an updated predictor, a linear predictor. Weight vector represents a predictor. So this is trial and error. We try out the predictor of the previous iteration this is the predictor from iteration k minus 1. This guy here. We try out We try out the predictor from the previous iteration, compute the error, and update the predictor from the current iteration, from the kth iteration. So this is the predictor iteration in iteration k. So gradient descent does learning by trial and error. You can find more details about this interpretation in the course book, as I said. So I highly recommend to read through the course book. Along we go in the course. Are there any questions? So gradient descent is a really powerful tool and the starting point of many, many current state-of-the-art methods in machine learning. They do learning by trial and error using gradient descent or variants of gradient descent. There's no magic about it. It's optimization. So, do you think this is, are we happy with this gradient descent now? I mean, how many of you think they could implement this update equation, this gradient descent machine learning algorithm in MATLAB or Python or C? Yeah, some. So, I mean, you have to compute the error, multiply the error with the vectors, add vectors. It looks very easy, very easy. How big is the sum here? N. How big is this? That depends on your training set. So if we use the quick draw training set, then N is 140,000. Is this a big training set? No, it's rather small. Imagine you work at Facebook, or you are a researcher at Facebook, even better, and you have a training set available where you get one data point from each Facebook user. You ask the Facebook users, in order to keep your Facebook profile, you have to draw an apple. So you get labeling by force. Then you have how many data points? Then capital N is millions, billions. So this sum might be impossible to compute. And remember, you have to do this sum in each iteration of gradient descent. And the number of iterations can be tens to thousands. So when you work at Facebook and force the users to do drawings of apples, you cannot really exploit all this labeled information in one iteration of gradient descent, because you cannot sum over billions of drawings which are stored, distributed in all Facebook servers over the world. So this sum here, this sum is a bottleneck often in machine learning. Computing this sum is difficult, can be very challenging in practice. Because N is large, N might be billions. Or the data points that you use here are stored distributed all over the world. You have to transfer the data points to one processing unit first before you do the sum. So what can you do? How can you cope with complexity? There's a nice idea to cope with complexity. The complexity here is to compute the sum of many, many terms. Another issue of complexity is for me to make sure that the grades are given fair in this course. We have now 830 students enrolled. Not all of them are here, as I see. But this is a complexity problem. So what was my solution to cope with this complexity? Do you remember what I told you last lecture? How do I cope with this complexity of fair grading of 830 students? More stuff? Well, the problem is, yeah, I can give more stuff, but I want to make sure that there are no free riders which just copy-paste solutions from others. How can I make this sure? I mean, one way to make it sure is to do an oral exam for everybody, for 830 students. So this is a complexity problem. So what did I do? Randomness. I said I randomly pick 10 to 20% of you, and they have to explain their solution by a Skype meeting or face-to-face here. So I use randomness to cope with complexity. And the same here in gradient descent. You can use randomness to get a method called stochastic gradient descent. And this works as follows. In each iteration, instead of computing the sum over all labeled data points, you pick a few labeled data points. In the extreme case, only one. Let's say this is the data point with index I. So xi, yi. So y is drawn randomly out of all indices of the data points, so 1 to n, and replace the gradient by an approximation, by a noisy approximation of the gradient, which is just the term of one corresponding to this one data point. So this is yi minus w transposed xi. So this capital I here is a random index. Important word here, random. Randomness is the key. The same as for my problem here to ensure the quality of the grades. If I would tell you which students I would pick, which 10%, it would not help me in any way to solve the problem. However, if I pick it randomly and you don't know which random generator I use, I'm able to cope with the complexity. I'm pretty sure all of you are now well prepared. And here the same, we pick the index at random, and instead of this whole sum, we only compute the sum over the randomly selected data points. And what stochastic gradient descent then looks is following. The iteration has the similar, so we start with an initial guess, and we again have an update rule, so we take the previous guess and then update, and instead of the full-blown gradient, we just plug in one randomly selected sample, or the contribution of one randomly selected sample. So this is k minus 1 transposed xi, and here we have xi. I have written this more clear in the course book again. So this is called stochastic gradient descent. And the complexity reduced from computing the sum over billions of data points to evaluating one data point selected at random. Pretty cool. You might want to try it out at some example. Generate some labeled data set. Actually, on Monday, next Monday, we release the next coding assignment, which is called Round 2, Regression. There you are asked to read in some labeled data and apply linear regression. You might have to implement this sum for gradient descent, and you might then try out just randomly selecting one component of the sum and do stochastic gradient descent. how much difference in performance do you get? Yes? So the yeah, the question was, do we have some pre-processing for the data or feature engineering to use stochastic gradient descent? So this is a different issue. Stochastic gradient descent is kind of the method that you use to search over this hypothesis space, and this hypothesis space contains functions from feature space to label space. So you can use different combinations. You can use stochastic gradient descent with whatever features you want. These are different aspects, but which typically play together in the end. But per se, using stochastic gradient descent does not require you any more feature engineering than gradient descent. Okay. Any other questions? Yes? Yeah, here only one. So this is the extreme case of only one. There is also batch stochastic gradient descent, where you use a subset of, let's say, k indices, I1 up to, or let's say, capital I to capital K, and there you replace this with an average over the batch size. So alpha over K times sum I1 and so on and so forth. And here you have the components for these indices. Yeah. So this is the extreme case where the batch size is 1. Yeah. Any other questions? Yes? Yes. So these indices have to be selected at random. But there are more than one randomly selected indices. Any other questions? Yeah?
Regarding data that is it also need able, data that is labeled like not an apple as well? So we have all this data that's labeled as an apple. Don't you also need like random drawings in order to do this optimization?
No, so the question was, do we only need labeled data or also some random drawings? Well, up to this point, yeah.
Like data that's also like not an apple, so you can have a label of not an apple and then a label of apple, right?
So the question was, what is good training data? And is it good to only have as training data apples? Well, it depends on your application. If you're only interested in finding the confidence that the drawing is an apple, then this might be good. If you want to discriminate between apples and something that is completely different than an apple, then you might need also training data points which show something else, like, what do we have here? Yeah, some other drawings. This depends on your application. Any other questions? Yeah. So how does the batch size affect the performance of stochastic gradient descent? So the batch size has two effects. First, the more you use, the larger batch size you use, the better your approximation gets to the true gradient. So the extreme case is where the batch size is the whole training data set, and then stochastic gradient descent becomes gradient descent. On the other hand, the batch size determines the computational complexity that you have. So this is kind of, the batch size allows you to go continuously between stochastic gradient descent with one sample, so no summation at all the way to full gradient descent. And then you have to tune based on your resources that you have, what you can afford, what batch size. Yeah? So the question was, if we have time series data, so if these data points, xi and yi, are time series data, is it also possible to use stochastic gradient descent? And this depends on the particular type of time series. If there's a lot of correlation, then you might have to be careful with how you select this random index. So this, what I told now, assumes no time structure of the data points. They are just anybody at some time draw an apple. But if you have a certain correlation structure in the data, then you need to be more careful with this, how to apply stochastic gradient descent. But this is more advanced, of course. Any other questions? Okay, so then we are ready to go into the weekend. Next week on Tuesday, I will have a similar lecture and talk about classification. We want to find out apple or no apple. Thank you.